let's start. Good afternoon, everyone. I'm Mingpu from Shanghai Jiaotong University in China. So first, I would like to thank the organizers for this opportunity to show our results on the Hubbard model. So today, I will talk about the study of two-dimensional Hubbard model within the SAMS collaboration and the Many Electron Problem. So that is outline. First, I will give you a very brief introduction of Hubbard model and the high-TZ conductivity. Then I will show our results. The results consist of 3 parts. The first one, I will talk about our first collaboration benchmark work. Then I will talk about the stripe phase in the 1A stop regime. And the last part, I will talk about our ongoing work on the superconducting pairing results. So let me give you a very brief introduction of Hubbard model. So the Hamiltonian of Hubbard model is like this. It consists of 2 parts, the kinetic energy part and the potential energy part. So the kinetic energy part describes the hopping of electrons and lattice. The potential energy part means if 2 electrons with opposite spins are on the same side, there is an increase of energy of U. So it's now widely believed Hubbard model captures the physics of high-TZ superconductivity. So I use believe here because, as you can see, the Hamiltonian of this model is very simple, but there is no analytical solution of this model. So and there are difficulties in numeric simulations. So in principle, if you want to study the correlated superconductor, it should involve 3 bonds, the D bond from copper and the 2 p orbitals from oxygen. But in this paper, Zhang and Rice derived a 1-bond effective model from this 3-bond Hamiltonian because of the hybridization of the copper and the oxygen orbitals. So before I show you some result, let me give a broader view of the difficulty in correlated quantum many systems. So I think many of us know the study of correlated quantum many body systems suffers from the exponential wall, which means the Hilbert space dimension scales exponentially with system size and the particle number. That means if we want to study these systems with brute force, for example, exact diagonalization, then the system size we can handle is very limited. For example, if we want to study spin 1/2 models, the largest system size we can handle today is about 14 size. For Hubbard model, if we want to study Hubbard model near halfway, which is the most interesting regime. So the largest system size we can handle is about 20 size. So this is based on if we only want to study ground state. If we want to study excited states, for example, if we want to calculate thermal quantities, we basically need information for all energy levels. Then in this case, the system size we can handle is even smaller. So here I show you an example of exact diagonalization. I think this represents the largest system size people can handle today. So this is a work by Andreas Noschen from Innsbruck. So each system is 48 cluster on Kagome lattice for the spin 1/2 Heisenberg model. So so we can ignore the detail here. Basically, these dots are the eigenvalues of this cluster, and this axis is different symmetry sector. So for this system, the whole Hilbert space dimension is this number, and because we have symmetries, we can divide the whole Hilbert space into different symmetry sectors. Even with these symmetries, the largest sector, the dimension for the largest sector is this number. You can see how large is these numbers if you want to use exact diagonalization to study these models. Of course, in this morning we have heard many effective methods to simulate quantum strong correlated quantum many-body systems, but I think it's fair to say we still need new method and new understanding on these systems. So that's why we are here today. So let me go to the results. So here is our collaboration and so here is the groups involved in this first benchmark paper on Hubbard model within the science collaboration. So the goal of this collaboration is we put groups working on different methods together to working on some basic models. So the goal is to try to understand what we know about these basic models and what's the strengths and weakness of different methods and different regimes of this model. So as we can see, we have 9 methods here. We have DMRG method, which was mentioned in this morning's lecture, and we have it's basically a Hartree fork method, and this is a method which is commonly used in quantum chemistry. And we have diagrammatic Monte Carlo, which basically sample the Feynman diagram, and we have DCA, DMET, which are inverting method, and we also have rational Monte Carlo and fixed load diffusion Monte Carlo. So this is the group I'm from. So we work on auxiliary field quantum Monte Carlo method. So as we learned this morning, there is a sign problem in QMC. So so in our group, we use a method which the sign problem is controlled, but with approximation. So I will not show any details of this method in this talk. So if you are interested, I will discuss the method in next Monday's symposium. So let me show you some results in this benchmark work. So this is the in this plot, I show you the energy, the ground state energy for the half-failing Hubbard model at U equal 8. So for different methods here. So you can see here, for each method we have finite size energy, and we also do extrapolation of the energy to infinite system size to get the thermodynamic limit value of ground state energy. So we can see we have, so this is for fixed load diffusion Monte Carlo results, and this is the extrapolated value. And we have DMRG for different So in DMRG we deal with cylinders, so we have result for different widths of the cylinder, and we have DMET for different supercell. So because at half fading there is no sign problem in QMC, so basically this value can be used as a benchmark for other methods. So we also have dynamic properties for Hubbard model. So in the left is the real part of the surface energy at U equal 8 and temperature T equal 0.5, which is pretty high. So we can show the agreements between different methods. And in the right part, I show the imaginary time of the local surface energy for the frequency. So we can see the agreements here, because here the temperature is pretty high and the density is pretty low. So we also provide a table for ground state energies and double occupants at T equals 0 for different methods and for a range of U values. So I think these values are very useful if you want to develop new method, you want to do some comparison to test the accuracy of the new method. So as I just mentioned, at half fading there is no sign problem for quantum mechanical simulation, but in order to get the thermodynamic limit value of ground state energy, we need to do an extrapolation of system size. So here I show you the extrapolation of system size for 4 different U values, and for each U values there are 3 lines here representing different boundary conditions. So the black symbols are for periodic boundary conditions, and the blue star are for periodic, anti-periodic boundary conditions, and the red lines are for twist average boundary conditions. So as we can see from these plots, so the twist average boundary conditions gives us a very nice finite size behavior. So this allows us to do a reliable extrapolation of system size to obtain the ground state energy at the thermodynamic limit. So the idea of twist average boundary condition is like for choosing system size, we add twist. We choose a set of twist boundary conditions, and we do the simulation for all these twists, and then we do an average to get the value. So we also provide finite size data for ground state energy and potential energy and kinetic energy for different U values and system sizes. So if you want to develop new method, you want some benchmark, you can look at this table. These values are for half field Hubbard model. So basically these are numeric exact results. So let's have a look at the one-way doping here. So here I show you the energy versus T for one-way doping Hubbard model at U equal 8. So we only have finite temperature values for DCA, and for ground state calculation we have result from different methods. That's here. In this insert, we zoom in this regime and put put the result from different methods on different x-axis. So as we can see here, we have large discrepancies for ground state energies from different methods. So I want to emphasize here because when you adopt the Hubbard model, there is sign problem for AFQMC. So here the result is so there is an error in this result. So
excuse me, does this method AFQMC satisfy the variation principle?
No, because we use the mixed estimate to calculate the energy. So
I see.
so that means that doesn't mean lower is better.
I see.
So it's possible that this value is known and the exact answer. So, but DMRG is variation. So let me summarize the first collaboration work on the Hubbard model. So we provide benchmark for the two-dimensional Hubbard model. And in this work, you can find strengths and weaknesses of different methods for different parameter regimes in Hubbard model. So there is a problem in the first collaboration work. So we didn't discuss about physical properties. We just provide numbers for basic quantities for these two-dimensional Hubbard model. So this is to the next collaboration work. So the second part of the result is about the stripe phase in the 1s doped two-dimensional Hubbard model. So as I just mentioned, at 1s doping there is a very large discrepancy among different methods. And if you have done a simulation about Hubbard model before, you will know 1s doping is the hardest doping for your simulation, which means if you do quantum Minicado, the average sign for this doping is the smallest. And if you do DMRG, the entanglement entropy at this doping is maximum. So before I show you the result, let me discuss a little bit more about the Hubbard model and TJ model and Heisenberg model. So here is the Hamiltonian of Hubbard model. So we can prove in a large unit if we don't allow double occupancy in the Hilbert space, we can get the low energy effective model, which is the TJ model, and the J is positive if the U is positive. So yeah. So at half filling, which means we have one electron per size, and the charge degree of freedom is frozen. We get the Heisenberg model. So here I show you a result for the static magnetic structure fractal from both simulation of 2D Heisenberg model and from experiment for this correlated superconductor. So the Fourier square are from the numeric calculation of the two-dimensional Hubbard model, Heisenberg model, and the Fourier cycles are from experiment. So we can see agreements between the simulation of 2D Heisenberg model and the experiment, which is evidence that the Hubbard model can describe the physics of correlated superconductor. So, and here is a work from Professor Anders Sandvik. So here the result shows at the for the Heisenberg model and square lattice, there is a long-range near order. So here is a finite size scaling of the longest correlation function for for spin. So we can see we go to the thermodynamic limits. We have a finite value here, which means we have a finite F momentum in this model. So here I show you hand-waving arguments about what will happen if we dope the near order. So here is a near order like this. So the spins aligns anti-ferromagnetically. So if we dope a hole into this near order, so which means we remove an electron, for example, in this site, so then the hole can hop in this lattice. So, for example, if the hole hops following this trajectory, then the resulting spin pattern is like this. So we can see there, because the exchange, the J here is anti-ferromagnetic. So we can see here, if the two electrons are in the same direction, that means there is frustration here and here. So this will cause energy. So we can think of two ways to load the energy. The first one is the so-called superconducting. So if two holes hop together, then there will be no frustration as shown here. So the other way is the so-called stripe state. So in the stripe state, the holes aligns in a line like this. So the hole can hop in the river of holes without destroying the anti-ferromagnetic background. So these are two possible consequences if we dope the near order. So of course this is just some hand-waving arguments. So let me go to the experiment. So shortly after the discovery of the first cuprate superconductor, people find that in this material at 1s doping, if we look at the transition temperature, there is a minimum here. So later on, people use other experiment techniques determine the stripe structure at the 1s doping. So the stripe structure is like this. The holes are concentrated on lines, and between two stripe, the electrons are anti-ferromagnetic. So here is a phase diagram for a high TC superconductor. So we can see close to the superconducting dome here, there are spin under charge fluctuations. So at least some people believe spin under charge fluctuation might be one way to understand the mechanism of ITC superconductor. So here is the present state of the study of 1s doped Hubbard model with different methods. So for DMRG method, people find the stripe and sometimes find the superconductivity. For diffusion and the variational Monte Carlo, people sometimes find phase separation, and in other works, people find superconductivity. For embedding method, for example, DMFT and DCA, people usually find the superconductivities in the 1s doped Hubbard model. For recent IPERPS work, people find the existence of superconductivity on a stripe. And for the constraint path AFQMC method, which is the method I worked on. So in our early work, we find a spin density wave and a stripe. So what I want to see here is that we have contradictory conclusions from different methods. So here I just list part of the result in the literature. There are many other results from other different methods. So here is the results we get from our method. So here I show you the staggered spin density and the whole density in this plot. So the red line is for the staggered spin density and the blue line is for the whole density. So as we can see, this is I think this is a 16 by 32 system. So as we can see here, we have if we look at the stacked spin density, so there is so in this regime is perfect anti-flat magnet. So if the result crosses 0 here, so that means there is a pi phase shift here, and also in this region is perfect anti-flat magnet. And also at the pi phase shift place, the whole density is maximum. So this is the structure of stripe. And in this plot, we show a color map of the spin density.
Excuse me, I have a question, naive question. The horizontal axis of the upper figure, the number of the sides?
Yes.
What is 0?
Oh, so you can label it from 0 to
Sorry,
1.
I see that. Yeah.
So you use a cylinder type geometry for this calculation?
Yeah. So the geometry is like this. It's a cylinder. So
impose the periodic boundary condition for one direction, the open boundary condition for the other direction.
yes.
That's the reason why the
Yeah.
quantity changes with size.
So yes. So in this setup we break the translational symmetry in this direction. So there is a reason why we choose this configuration. So first, at the early stage of this project, we want to compare with DMRG. So in DMRG, we can only deal with this cylinder geometry. So we can't afford to deal with periodic boundary conditions in both directions for DMRG. And actually, we also did some calculation with both periodic boundary conditions. So in that calculation, we need to calculate the density correlation function. And we also see some structure like this, but there is a technical reason so why we choose this configuration, this setup, because in quantum in QMC calculation, if you want to calculate the correlation function, the number is very small, so the fluctuation is very large. So here is a kind of fish I caught when I was in Virginia. So the name of this fish is striped bass. So you can see the same patterns here. So in this work, so we have 4 different methods working on the ground states at one doping. So basically, so let me explain the plot here. So the arrow direction here means the spin direction, the up and down, and the arrow size means the spin density. And there are circles here. The arrow of these circles means the whole density. So as we can see from this, so these are result from four different methods. So this is for DMET, this is for QMC, and this is for IPREPS, and this is for DMRG. So we find agreements for the spin and the charge patterns for this one-S doping. But as you can see, there are some discrepancies on the details. For example, the hole density and the spin density, but the stripe pattern is the same.
Also, for this, can I ask the size of the system for these four methods? I think they should be different.
Yes. Okay. So for DMET, so this is basically the unit cell. Because it's an inverting method, so they have like a unit cell, and they have basically then you can think of the repeat of this unit cell. So it's a thermodynamic. They deal directly with infinite size systems. So this is the size of the unit cell, and from this is for our AFQMC calculation. I think the largest system size is from this 16 by 32, and for IPREPS, so it's they deal directly with thermodynamic limit. So have a unit cell like this, and for DMRG, I think they deal with cylinder. So the width I think the width of the cylinder they can reach is 6. So it's 6 by, you can think this the long direction is infinite. So here I show you the ground state energy for different methods at one-S doping for different methods. So these are energies from thermodynamic limit. So we do some extrapolation of system size or unit cell for different methods. So as we can see, we have agreements around this shadow area. So in the insert, we show the half-filling case. We have a better agreement at half-filling. So you may ask, why do we need different methods? As I just mentioned in the early part, earlier, because there are strengths and limitations for different numerical methods. So it's fair to say today there is no perfect method for two-dimensional strong correlated systems. So for example, for DMRG, it's perfect for 1D system, but for two-dimensional system, the state need to increase exponentially with the width of the system if you want to keep the accuracy of your calculation. That means the width of cylinder you can deal with is very limited. And for IPREPS, as we learned in this morning's lecture, the IPREPS can capture the entanglement entropy of the two-dimensional system, but due to the very large scaling with the bound dimension, so at present the bound dimension can reach in this method is very limited. So with this limited bound dimension, we can't get a reliable scaling with this bound dimension D. So for DMET, so they deal with infinite system directly, but we need to do an extrapolation of the unit cell size for our QMC method. So basically, our calculation doesn't depend on the dimension of the system, but as I will show in next Monday's talk, we get rid of the sign problem, but we suffer from the constraint error. So here I show you an example to to show the complementary of DMRG and AFQMC. So we have two systems here. So these results are basically for DMRG. So these two curves are for 16 by 6 system with similar geometry. So in our QMC calculation for these two systems, we always find the 6-hole stripe. But in DMRG calculation, so here this is, you can see, you can view this as a truncation error in the DMRG calculation. So if we go this way, the truncation error becomes smaller and the bond dimension becomes larger. So for DMRG calculation, they first find that the 4-hole stripe has low energy, as the result shown here. So if we increase the bond dimension, so if we go this way, there is a cross between these two states. So then in the large bond dimension, the 6-hole state becomes the true ground state energy.
Now, excuse me, which one is the DMRG result and which one is
so these plots are all about DMRG results.
Oh, I see.
Yeah. So these two lines are for 16 by 6 system, and these are for 32 by 6 system. So different symbols represent a stripe state, different type of stripe states. So you can see there is a crossover energy with the increase of bond dimension.
Oh, I see.
Excuse me. Can we fix the number of hole in the DMRG optimization?
And the number of holes?
Yeah, number of holes. So 4 holes and 6 holes are.
Oh yeah. So basically, you can start your DMRG calculation with some initial states.
Yes.
Yeah.
Then this initial state, I mean, such a character is kept during the optimization.
I know what you mean. So the total hole number is fixed. So we work on fixed number calculation. But here the 4-hole means the number of holes in one stripe. That means for these two states, the wavelength of the stripe is different. But the total number of holes is fixed. So these are all about one distortion case. So here I show you the results of energy for different for stripe states with different wavelengths and for different methods. As we can see here, for different for stripe states with different wavelengths, the energy is almost degenerate from 5 to 8 or 9. So that means the stripe state in our calculation is not rigid. That means the wavelength of the stripe can fluctuate without causing energy.
So in infinite system, anyway, the system is gapless.
I don't know.
I think so.
Yeah,
Cross-section symmetry is broken?
Yeah, and also the magnetic correlation should show some magnetic components. So therefore, it's no wonder that the ground state is degenerate. Right?
Yeah. So we didn't, unfortunately, we didn't calculate the gap directly in our calculation. I think there are some difficulties in calculating. Yeah. So here comes my conclusion. So in the science calibration of many electron problems, we provide benchmark for two-dimensional Hubbard model. So this is very useful if you want to develop new methods, or if you want to look at the strengths and weakness of existing method. And we establish stripe state, its ground state of the one is the two-dimensional Hubbard model. And it seems there is no Lagrange pairing at this doping. So I want to emphasize that because we studied the pure Hubbard model, so in our work, so the absence of long-range order pairing in our calculation indicates if you want to have long-range pairing in Hubbard model, you might need to increase add some other terms, for example, the T prime hopping term into this model. So this is the collaborators. So most of the DMRG calculation for the pairing is by Chamin Zhang, who was a postdoc in Steven White's group before, and now he moves to Wunni's group in Munich. Okay. Thank you.